Hey there, geometers. In this lesson, lesson 10.3.3, we are going to be focusing on combinations. We are going to look at how many groups are possible, but maybe where the arrangement does not matter. Before you looked at how many different ways you could count permutations, and that was where the order was important. In this case, we're going to look at things such as how many committee members can be selected or how many poker hands there are, winning the lottery. In all of these situations where the committee members maybe have equal status, or you just want the lottery numbers on your winning lottery ticket where the order does not matter, we're going to talk about how to mathematically calculate the number of combinations, which is an arrangement where the order does not matter. In this first problem, we'll look at the difference between a combination and a permutation. 5 members of the Spirit Club have volunteered for the governing board. These members are Al, Barbara, Carl, Dale, and Ernie. The club members will select 3 of the 5 as board members for the next year. One way to do this would be to elect a governing committee of 3 in which all members would have the same title or equal status. A second way would be to select a president, vice president, and secretary. Part A, how many different lineups of officers are possible? This means a president, vice president, and a secretary are chosen. Thus, Al as president, Barbara as vice president, and Carl as secretary would be a different possibility from Al as president, Barbara as secretary, and Carl as vice president. In this first situation, order matters. So if I were to do this using the permutations that you learned in the previous video, I would have 3 spots in my decision chart, and I would have 5 choices for the first position. After that one person or one selection was made, I would then have 4 choices for my second position, and then 3 choices after that, giving me a total of 60 different possibilities if they were ranked. Now, part B of this question is where it gets especially interesting. Part B says how many different 3-member committees are possible. In this case, it is a good idea to make a list of all the possibilities, which are called combinations. Now, in this case, it doesn't matter whether your name is first, second, or third because each person on this committee would have equal status. So when I make my list, I'm going to make my list in a systematic way. I'm going to list A, B, and C together. Remember, that's Al, Barbara, and Carl. Then I'm going to list Al and Barbara, but just replace the third member. So I'm going to go through all my AB possibilities, then all my AC possibilities, AD. Then I'm going to go through my next column and leave Al off all the groups. So I'm going to go through my BC and my BD, and then finally my CD until I have all possibilities. Now, when I compare this to the number of possibilities in Part A, I see that it is quite a bit less, and we'll look more at that later. Then Felicia comes along, and Felicia decides that she wants to volunteer as well. How many different possibilities for officers are possible now? Well, if I'm having officers and having the different ranks, now instead of having 5 choices for the first position, I would have 6 choices. So my new permutation is going to be 6 times 5 times 4 using my decision chart, or using my permutations formula, 6 factorial over 3 factorial. Now I have 120 different possibilities. How many different governing committees are possible now? Again, that would be equal status, and I'm going to make a list. So actually what I'm going to do is I'm going to take the previous list that I already had made, and I'm just going to add the possibilities that include Felicia. It doesn't change a whole lot, but you can see that it does add several more possibilities to that list. Now let's change things up one more time and see if we can notice a pattern here. Since there are more volunteers, the Spirit Club has decided to appoint another committee member. Okay, so now there's more volunteers, they're going to appoint another committee member. So if they add a treasurer to the list of officers, how many different ways are there to select the 4 officers? So now my decision chart is going to have 4 spots, and I'm going to have 6 people to choose from for the first row, and then 5 for the row after that, times 4 times 3. That's going to give me a total of 360 different possibilities. If they're going to choose a governing committee of 4, there's going to be significantly less possibilities. So again, I'm going to make my list in strategic order. I'm going to just go in order A, B, C, D, and then I'm going to throw D out and I'm going to do A, B, C, E, So I'm going to work my way through all of the AB combinations, then the AC, AD, and I can make this list, but eventually I'll want to find a different way to come up with this answer. So now we're going to take a look at the numbers and see how permutations and combinations relate to each other. We're going to go back to the problems we had before. Now, in the first example that we did, we had 5 people and we were choosing a group of 3. Now, when they were ranked, that was a permutation and there were 60 possibilities. When I was doing my combinations, where I was just choosing a committee and they all had equal status, I only got 10 combinations. Part C was when Felicia joined in, and then I was choosing 3 people from a group of 6. When order mattered, I had 120 possibilities. And then for the combinations there, I only had 20. So that one changed by a factor of 6, whereas the one above decreased also, I guess, by a factor of 6. Now, when I look at Part D, I had more volunteers. The Spirit Club had another committee member, so then I had 360 ways that I could choose the 4 officers from the 6 people. And when I made that into a combination instead of a permutation, I only had 15. So I'm looking for ways that these relate to each other. So now as I look at these, I'm looking for a relationship here between the number of permutations and the number of combinations. And what I notice here is that when I was choosing 3 objects or 3 people from the group, the permutations and combinations differed by a factor of 6. When I was choosing 4 members, it differed by a factor of 24. So I'm curious, what is it about the choosing of 3 members that makes it differ by a factor of 6? But also the same reason that when I choose 4 members makes it differ by a factor of 24. If I think about this in terms of factorials, 3 factorial is 6. Or the way that I can arrange those 3 people, I have 6 different ways that I can arrange them. So if order doesn't matter, for the first one when I'm choosing 3 people, my combination is going to differ from my permutation by the ways that I can arrange those 3 people, which is 3 factorial or 6. Similarly, if I'm choosing 4 people and the order does not matter, my combination is going to be smaller than my permutations by a factor of however many ways I can arrange those 4 people, which in this case is 4 factorial or 24. So let's test this theory by calculating the number of permutations and combinations of 2 items chosen from 6. Using my permutation notation from the previous video, I know that I'm going to be choosing 2 items. I'm going to have 6 choices for the first one and 5 for the second, giving me 30 total possibilities. Now, if I look at combinations, I would need to divide that by the number of ways that I can arrange those 2 items. Now, if I wanted to figure that out, I would just put my decision chart in the bottom. The ways that I can arrange 2 items would be I would have 2 choices for the first and then only 1 choice for the second. So I should have 15 combinations. One way to double check that would just be to number off 6 items and then make a list of all the ways that I can choose 2 if order doesn't matter. And as you can see by looking at this example, this method works. I made my list, I got 15. I looked at the combinations first and I said, all right, it's 30 permutations. If I divide that by the ways that I can arrange them, that also gives me 15. So I have a mathematical formula, so I don't have to go about making all of these lists, even though, you know, it's super fun to do so. So I'm going to write a rule that relates the number of permutations to the number of combinations. I'm going to find my number of combinations by first calculating the number of permutations and then dividing by the number of ways that the items that I'm choosing can be arranged. So I'm going to take my permutations formula from the previous video and I'm going to divide that by r factorial. A simplified version of the formula is written here. Remember that n is the number of items that we have to choose from, and then r is the number of items that we are actually choosing. This can be often read as n choose r, or in the case of our last example, 6 choose 2 is how we would read that. All right, now we can use our formula to go ahead and calculate some combinations. In one state lottery, there are 56 numbers from which a player can choose 6. Does the order in which the numbers are chosen matter? For this particular example, no. I just want to have the winning numbers on my ticket. So I'm going to find the number of possible combinations for a set of 6 winning lottery numbers. So I'm going to go about this by using my permutation formula and then dividing it by 6 factorial, because that's the number of ways that these items can be arranged. That will give me the total number of combinations for that winning lottery ticket. And then for part C, what is the probability of selecting the 6 winning numbers? Well, it would be 1 out of that total, or 1 out of 32,468,436. All right, so let's look at an application again. In the game of poker called 5-card draw, each player is dealt 5 cards from a standard deck of 52 cards. While players tend to arrange the cards in their hands, the order in which they get them does not matter. How many 5-card poker hands are possible? Use the methods you developed in today's investigation to answer this question. So the first thing I'm going to do is write it out like I would a permutation. I would make my decision chart, and then I would have 52 choices for my first card. And then because that one's already in my hand, I would have 51 choices for the second, and so on until I have the possibilities for all 5 cards in my hands. Now, because the order that I get the cards does not matter, I need to divide that by the ways that those 5 cards can be arranged, which is 5 factorial. Or I could plug it into my formula and list out the 52 factorial over 47 factorial and then divide by the 5 factorial there. Either way, they should give me the same result in finding the total number of possible 5-card poker hands using the 5-card draw game. So to recap, when selecting committees, it matters who is selected, but the order of selection or arrangement of the groups doesn't matter. So committees, other lists or groups where the order doesn't matter, or there's no regard to the order within the group, or maybe they all have equal status, are called combinations. Combinations do not allow for repetition of the elements. And they give you a couple examples here. So if 8 people are eligible to receive the $500 scholarships, but only 3 will be selected, how many different ways are there to select the group of 3? You don't care whether you're selected first or last. Either way, you're still going to get that $500 scholarship. Again, we can see this notation here and how it is sometimes read as 8, choose 3. So to review, we first calculate the number of permutations and then divide by the number of ways that those can be arranged. So I'm going to take the number of ways to choose them and arrange them and divide them by the number of ways that can be arranged, or use this formula here. You'll want to make sure you pause the video, make sure you have that formula written down in your notes. We will come back to that tomorrow as we practice these. Thanks for watching.